Before we start building our own LED backlight tester, let us explain what is and how does a backlight tester works. In simple terms, an LED backlight tester is a constant current source. It is a power source which only allows a specific current despite in change of resistance of the load. Conventional and switch mode power supplies, on the other hand, only allows a specific voltage while allowing change of output current. To create the cheapest and simple LED backlight tester, we will only need an LED bulb and wires. You'll also going to need a soldering iron and a soldering lead. You can also add a switch if you can get one. Just a single pole, single throw switch will do the work. The LED bulb that we have has a damaged LED. You can also use a broken LED bulb as long as the rectifier, capacitors, and resistors are not damaged. The wires we used are just speaker wires as probes. We got the wires and switch from an old project of mine. You can start by opening the LED bulb by cutting it or by slowly pressing the sides to remove the glue of the cover. If you want to attach a switch, you can slowly remove the board and attach the switch in between on one of the wires underneath. We used excess wires to extend the wires to the switch and attach the switch on the bulb. To connect the probes, you need to identify where is the end of the power supply and resistors. The circuit usually is as simple as two resistors, one in parallel and one in series of the power supply. One end of your probe should be connected at the end of the resistor in series, while the other is connected on the other end of the resistor in parallel. You also need to remember that you can use the capacitor in parallel to know which side is positive and negative. Before closing the bulb, we also partially fixed the LED circuit by connecting a different LED for indication and connected a plug to be able to easily use it. We also soldered the tip of the wire probes to be able to use it just like a multimeter probe. While this does work, this is not as powerful or as convenient as an actual backlight tester. So, let's build one from scratch. Step 1 in making your own backlight tester from scratch is by creating it as a concept using theories and formulas. We can start at powering the tester. One of our ideas is to use batteries as its power source can make it more efficient and requires no connection to the city power lines. But batteries can only have a very small voltage. Even when you series a lot of batteries, you will still need a BMS that is capable of managing many batteries. So the only choice is to use the 220 volt AC as our main source. Next is to convert it into DC using a full bridge rectifier to turn it into a DC pulse and a capacitor to smoothen it. Then to the backlight tester. Since we already have a DC power source of around 300 volts, we only need to create a constant current source. One simple way to do this is the same as the circuit in LED bulbs, using resistors in parallel and in series. To get the resistance of each resistor we need, we first need to get the total resistance. It's simply using the Ohm's law. Voltage is equals to resistance times current. For our total voltage, we'll use 311 volts and 0.02 amperes for the total current. We'll be able to get the value of 15,550 ohms. For simplicity, we'll just use this for the resistor in series. For the resistor in parallel, we need to use a load as a reference. Assuming the load needs 150 volts and 0.02 amperes, we can again get the resistance using the Ohm's law. And we get 7,500 ohms. Since we now already got every information we need, we can now combine the Ohm's law, series, and parallel resistance formulas to get the value of the resistor. Applying the formula we made on the values we previously used, and we get the resistance value of 42,950 ohms. Before we actually create this circuit, let me just be very clear that one of the goals of this version of Backlight Tester is to get the largest possible range of voltage while still making the circuit as simple as possible. So, we will also add a potentiometer which will allow us to test small LEDs and then switch to short a small part of our parallel resistor to also allow higher current output, which is around 0.03 amperes. Step 2 is planning the circuit by making the PCB. The resistor we used are rated for 2 watts, but my personal recommendation is it should be at least around 5 watts. From the ECEDA website, we can print the parts that we only want, which are copper tracings and the board outline. I'll be using a pre-sensitized PCB as my board, since pre-sensitized PCBs can be as accurate as factory manufactured PCB. Using the paper layout of the copper tracing, we can use this to only expose the parts of the board we need using an exposure box. To remove the exposed coating, we use a PCB developer to remove it. Now, the copper areas are now exposed. We can remove it using ferric chloride. To remove the excess coating, we can simply use a cloth and acetone. We can then finish the board by drilling the necessary holes for the components. Step 3 is to simply solder the components needed for the circuit. This time, we'll use an actual probe for multimeters. I also added another switch and a fuse on my circuit on the AC source. We used a junction box as our enclosure for the circuit. Before we continue in testing the backlight tester, the values we have now isn't originally the intended resistance. The original resistance value we were going for was 15,500 ohms for the resistor in series, while 31,724.08 ohms for the resistor in parallel. The reason why these are the best values because these values can completely prevent the circuit from overvoltage and potentially overcurrent. I was able to get this value by cross-testing the most extremes, which are 300 volts and 1 volt. And if we use the resistance value using the other resistor from each other, then it's either it doesn't work or it breaks. But the value we can use is the one that came from 1 volt load, since we can simply add a resistor in parallel to decrease the resistance when attached on higher voltage load. And to get that value, it's almost the same as last time, but this time we will use the 300 volt on the load. This should consistently only reach between 0.021 amperes to 0.03 amperes on almost any given load. This is assuming that every load only needs 0.02 amperes, since that's the most common current for LED. After creating two different backlight tester, is it better designing or making your own backlight tester? Or should you just use your own broken bulb and use it as a backlight tester? Even though we wasted a lot of money on the second backlight tester, there is still a major advantage, which is preventing smaller LEDs to get damaged since you have full control on how much power you're giving the LED. It should also be possible to test higher voltage of LEDs by simply decreasing the resistance and increasing the current. While the cheapest backlight tester does work, it may break small LEDs just like what happened on one of my red LED. And it also takes time between testing multiple LEDs. Since the circuit in it is specifically designed for the LEDs on it, it wouldn't be capable of powering larger strips of LEDs. So considering all of the pros and cons, you should only make this if you just need a quick backlight tester, and create your own if you want to completely prevent damaging any LEDs and if you can afford it.